Hello everyone, welcome to my channel. This is an educational channel, and we look at great theories of everything from the past and go deep into them, and hopefully you can glean how you might be able to use these things in your own life to help you with your transition to 5D consciousness, your paradigm shifting and awakening to a holistic worldview. And today is our 512th video that we've done on the reciprocal system of theory from Dewey B. Larson. And in 1959, Mr. Larson proposed his two fundamental postulates about how he believed the universe operated. And from there, he derived a theoretical universe, how his universe would look if his postulates were correct. And then he compared his theoretical universe with the measured empirical universe of modern science that they have put down in their scientific tables. And we are looking at one of those books here that's called Basic Properties of Matter, primarily on chemistry, and Larson arrives at equations for many of the basic properties of matter and then compares them with the scientific tables, like the melting point and the specific heat. And we are about to start chapter 22 of this book on magnetic materials. Now, if you'd like a detailed description of Larson's reciprocal system, you want to watch one of my first 474 videos on this subject, where I go into the two fundamental postulates and explore the ramifications and the derivation of the theoretical universe. And but for the purposes of this video, I'm going to more or less assume that you have some background in the reciprocal system, or else you are comfortable just listening to a reading where you're not, you're a little bit in the dark about how everything is working, which could pay off because Larson does a lot of times explain himself within the chapters. So either way, I'm going to start here with chapter 22, Magnetic Materials. The discussion of static magnetism in chapter 19 was addressed to the type of two-dimensional rotational vibration known as ferromagnetism. This is the magnetism known to the general public, the magnetism of permanent magnets. As noted in that earlier discussion, ferromagnetism, that's F-E-R-R-O magnetism, is present in only a relatively small number of substances. And since this was the only type of magnetism known to the early investigators, magnetism was considered to be some special kind of phenomenon of limited scope. This general belief undoubtedly had a significant influence on the thinking that led to the conclusion that magnetism is a byproduct of electricity. More recently, however, it has been found that there is another type of magnetism that is much weaker, but is common to all kinds of matter. For an understanding of the nature of this second type of static magnetism, one needs to recall that the basic rotation of all material atoms is two-dimensional. It follows from the previously developed principles governing the combination of motions that a two-dimensional vibration a charge can be applied to this two-dimensional rotation. So a two-dimensional vibration, a charge, can be applied to this two-dimensional rotation. However, unlike the ferromagnetic charge, which is independent of the motion of the main body of the atom, this charge on the basic rotation of the atom is subject to electric rotation, subject to the electric rotation of the atom in the third scalar dimension. This does not alter the vibrational character of the charge, but it distributes the magnetic motion and the force over 3 dimensions and thus reduces its effective magnitude to the gravitational level. To distinguish this type of charge from the ferromagnetic charge, we will call it an internal magnetic charge. As we have seen, the numerical factor relating to the magnitudes of quantities differing by 1 scalar dimension in terms of CGS units is 3 times 10 to the 10th. The corresponding factor applicable to the interaction between a ferromagnetic charge and an internal magnetic charge is the square root of the product of 1 and 3 times 10 to the 10th, which amounts to 1.73 times 10 to the 5th. The internal magnetic effects are thus weaker than those due to ferromagnetism by about 10 to the 5th. The scalar direction of the internal magnetic charge, like that of all other electric and magnetic charges thus far discovered, is outward. All magnetic two-dimensional rotation of atoms is also positive net displacement in time in the material sector of the universe. But the motion in the third scalar dimension, the electric dimension, is positive in the division 1 and 2 elements and negative in the division 3 and 4 elements. As explained in Chapter 19, the all-positive magnetic rotations of the material sector have a polarity of a different type that is related to the directional distribution of the magnetic rotation. If an atom of an electropositive element is viewed from a given point in space, from above, for example, it is observed to have a specific magnetic rotational direction, clockwise or counterclockwise. The actual correlation with north and south has not yet been established, but for present purposes we may call the end of the atom that corresponds to the clockwise rotation its north pole. This is a general relation applying to all electropositive atoms. Because of the reversals at the unit levels, the north pole of an electronegative atom corresponds to the counterclockwise rotation. That is, this north pole occupies a position corresponding to that which is occupied by the south pole of an electropositive atom. When electropositive elements are subjected to the field of a magnet, the orientation of the poles is the same in both the atoms and the magnet, which is similarly positive. The atoms of these elements therefore tend to orient themselves with their magnetic axes parallel to the magnetic field and to move toward the stronger part of the field. That is, they are attracted by permanent magnets. Such substances are called paramagnetic, P-A-R-A, magnetic. Electronegative elements, which have the reverse polarity, are oriented with the poles of their atoms opposite to those of a magnet. This puts like poles together, causing repulsion. These atoms therefore tend to orient themselves perpendicular to the magnetic field and to move toward the weaker part of the field. Substances of this kind are called diamagnetic. In present-day magnetic theory, diamagnetism is regarded as a universal property of matter, the origin of which is unexplained. Quote, all materials are diamagnetic, says one textbook. On the basis of paramagnetism or ferromagnetism, where they exist, simply overpower paramagnetism or ferromagnetism, where they exist, simply overpower the basic diamagnetism. Our finding is that each substance is either paramagnetic or diamagnetic, depending on the scalar direction of the rotation in the electric dimension. Ferromagnetic substances are paramagnetic, with an additional two-dimensional rotational vibration of the kind previously described. All elements of the electropositive divisions 1 and 2, except beryllium and boron, are paramagnetic. As in the case of other properties previously discussed, the positive preference carries over into some of the adjoining elements of division 3. All other elements of the electronegative divisions of 3 and 4, except oxygen, are diamagnetic. The abnormal behavior of some of the elements of group 2A, beryllium, boron, and oxygen included in that, is a result of the small size of this 8-member group, which permits the constituent elements, in some instances, to function as members of the inverse division of the group. Boron, for example, is normally the 3rd member of the positive division of group 2A, but it can alternatively act as the 5th member of the negative division of this group. Boron and beryllium are the positive elements nearest to the negative division in this group, and therefore the most subject to whatever influences tend to cause the polarity reversal. Just why oxygen is the element of the negative division in which the polarity reversal takes place is not yet known. As brought out in Volume 1, all chemical compounds are combinations of electropositive and electronegative components. The presence of any significant amount of motion in time, space displacement, is in a molecular structure prevents establishment of the positive magnetic orientation. All compounds, except those that are ferromagnetic or heavily weighted with paramagnetic elements, are therefore diamagnetic. This overwhelming preference for diamagnetism in the compounds is probably what led to the currently accepted hypothesis of a universal diamagnetism. The intensity of the magnetic effect in a magnetic material is measured in terms of magnetization, symbol M, which was defined in Chapter 20. The magnetization and the intensity of the applied field are additive. Both, therefore, have the dimensions of magnetic field intensity, T squared over S to the 4th. But for historical reasons, the field intensity is customarily identified with the vector H, which has the dimensions of 1 over T. Since the magnetization must have the same dimensions as the field intensity, it is also expressed in terms of a unit with the 1 over T dimensions. As we saw in Chapter 20, the actual physical quantities are Greek letter M and Greek letter H rather than M and H. That Greek letter is referring to permeability, of the permeability entering into these definitions is the permeability of free space, which has unit magnitude. The dimensional error therefore does not affect the numerical results of the calculations. From the foregoing, the net total magnetic field intensity, B, is the sum of permeability 0, the permeability of free space times N, and permeability of free space times H. For some purposes, it is convenient to express this quantity in terms of H only. This is accomplished by introducing the magnetic susceptibility, X. Or I guess that's another Greek letter that looks like X, maybe psi. Defined by the relation psi equals m over h. On this basis, B equals the quantity 1 plus x times the permeability of free space times h. As indicated earlier, the internal magnetic effects are relatively weak. The susceptibilities of both paramagnetic and diamagnetic materials are therefore low. Those of the diamagnetic substances are also independent of temperature. Some studies of the factors that determine the magnitude of the internal magnetic susceptibility were undertaken in the early stages of the theoretical investigation, whose results are being here reported, and calculations of the diamagnetic susceptibilities of a number of simple organic compounds were included in the first edition of this work. These results have not yet been reviewed in the light of the more complete understanding of the nature of the magnetic phenomena that has been gained in the past several decades. But there are no obvious inconsistencies, and some consideration of these findings will be appropriate at this time. As would be expected, since the internal magnetic charge is a modification of the magnetic component of the rotational vibration of an atom, start this sentence over. As would be expected, since the internal magnetic charge is a modification of the magnetic component of the rotational motion of an atom, the magnetic susceptibility is the reciprocal of the effective magnetic rotational displacement. There are, of course, two possible values of this displacement for most elements, but the applicable value is often indicated by the environment. That is, association with elements of low displacement generally means that the lower value will prevail, and vice versa. Carbon, for instance, takes its secondary displacement, 1, in association with hydrogen, but changes to primary displacement, 2, in association with elements of the higher groups. Another source of variability is introduced by the fact that the susceptibility, like most other physical properties, has an initial level, and this level is also influenced by environmental factors. At the present stage of the investigation, we are not able to evaluate these factors from purely theoretical premises, but they vary in a fairly regular way in the various families of compounds. We can therefore establish what we may call semi-theoretical values of the diamagnetic susceptibility of many relatively simple organic compounds with the aid of series relationships. The experimental values of the susceptibility of these compounds vary over a substantial range. It was found, however, in the original investigation that except for certain differences in the initial levels, the diamagnetic susceptibility has the same value as a constant, which we are calling the refraction constant, that determines the index of refraction. The properties of radiation will not be covered in this volume, but the measurements of the refractive index are much more accurate than those of the magnetic susceptibility. It will therefore be desirable to use the refraction constant as a base calculation in the calculation of the susceptibilities, and some explanation of the manner in which that constant was derived will be required. Like the internal susceptibility, the refraction constant is the reciprocal of the effective magnetic rotational displacement, the total displacement minus the initial level. As in the case of the susceptibility, the determination of this constant is complicated by a variability in the initial levels, especially those of the most common elements in the organic compounds, carbon and hydrogen. For convenience, both in calculation and in emphasizing the series relationship, a value of the refraction constant is first calculated on the basis of what we may regard as normal values. The derivation of the constant from the normal value is then determined for each compound. Table 33 shows the derivation of the refraction factors in 3 representative organic families of compounds. In the acids, for example, the normal rotational displacement of the oxygen atoms and the carbon atom in the CO group is 2, while that of the hydrogen atoms and the remaining carbon atoms is 1. The normal initial level is 2/9 in all cases. The normal refraction factors of the individual rotational mass units are then 0.778 or 7/9 for the displacement 1 atoms, and half this value, 0.389, for those of displacement 2. All of the acids from acetic acid, carbon 2, to enanthic acid, C7, are inclusive, have normal initial levels, no deviations, and the differences in the individual refraction factors are due entirely to a higher proportion of the 0.778 units as the size of the molecule increases. The normal initial level in the corresponding hydrocarbons, however, is only 1/9. And when the molecular chain becomes long enough to free some of the hydrocarbon groups at the positive end of the molecule from the influence of the acid radical at the negative end, these groups revert to their normal initial levels as hydrocarbons, beginning with the CH3 end group and moving inward. In caprylic acid, C8, the 3 hydrogen atoms in the N group have made the change. Those in the adjoining CH2 group do likewise in pelargonic acid, C9. And as the length of the molecule increases, still further the hydrogen in initial CH2 groups follows suit. As the length of the molecule increases still further, the hydrogen in additional CH2 groups follows suit. Okay, so now he has a table where he's looking at all the acids, and I don't, he's comparing the theoretical value with the observed value. And he's got several values though here, not quite making heads or tails of this table yet, but it looks like his calculations calculated at 0.391, and the value is 0.393. 0.449 for caproic acid, and the value is 0.448. Enanthic acid, 0.459, observe 0.458, and paraffins, 0.581, calculated, observed 0.582. Going all the way through, heptane, octane, nonane, pentadecane, and so on. Calculates also the esters, and that also has that same initial level. And the calculations are all generally quite accurate. Certainly usually within 1 or 2 thousandths. I don't really even see any where there are any discrepancies more than a few thousandths. Okay. The deviations from the normal values expressed in numbers of 1/9 units per molecule are shown in the first column of table 33. The second column shows the refraction constants, Kr, calculated by applying the deviations in column 1 to the normal values. In columns 3 and 4, the product 0.697 Kr is compared with the quantity n-1 over d, where n is the refractive index at the sodium D wavelength and d is the density. The refraction constant is related to the natural unit wavelength rather than to the wavelength at which the measurements were made, but the difference is incorporated in the factor 0.697 that is applied before the comparison with the values derived from observation. An explanation of the derivation of this factor and the reason for making the correlation in this particular manner would require more discussion of radiation that is appropriate in this volume, but the status of the calculated refraction constants as specific functions of the composition of the compounds is evident. In the paraffins, the initial levels increase with increasing length of the molecule rather than decreasing as in the acids. As brought out in volume 1, the hydrocarbon molecules are not the symmetrical structures that their formula molecules would seem to represent. For example, the formula for propane, usually expressed is CH3, CH2, CH3, which indicates that the two end groups of the molecule are alike. But the analysis of this structure revealed that it is actually CH3, CH2, CH2H, with a positive CH3 group at one end and a negative hydrogen atom at the other. This negative hydrogen atom has a 0 initial level, and it exerts enough influence to eliminate the initial level in the hydrogen atoms of the two CH2 groups, giving the molecule a total of 5 units of deviation from the normal initial level. When another CH2 group is added to form butane, the relative effect of the negative hydrogen atom is reduced, and the 0 initial level is confined to the CH2H combination with 3 hydrogen atoms. The deviation continues on this basis up to pentadecane, C11, beyond which it is eliminated entirely, and the molecule as a whole takes the normal 8/9 refraction constant. Also shown in Table 33 is a representative sample of the monobasic esters, which, as would be expected of acid derivatives, follow the same pattern as the acids. The only new feature is the appearance of a -3 deviation in some of the lower compounds. This appears to be due to a reversal of the influences that are responsible for the additional positive deviations in the lower paraffins, an interpretation that is supported by the fact that both end groups of the esters are positive. The objective of Table 33 is merely to show how the refraction constants that are used in the susceptibility calculations are derived from the molecular composition and structure, and the number of compounds listed has been limited to those required for this purpose. The refraction constants used in application to the greater number and variety of compounds included in Table 34, which shows the kind of results that are obtained from the susceptibility calculations, are determined in the same manner. As noted earlier, the diamagnetic susceptibility of an organic compound is equal to its refraction constant, with an adjustment for a difference in the initial levels. The magnetic initial level is generally the same as that in refraction, except in certain groups in which the level is modified by some factor not yet specifically identified, but apparently geometric. In the compounds listed in Table 34, the CH3, CH2OH, and OHN groups have initial levels 1/9 unit higher per unit of rotational mass than the refraction levels. Interior CH2 groups are subject to a similar modification, half as large at certain points as the molecular chains lengthen. The sum of the individual differences in initial level, delta I, is m prime over 9, where m prime is the number of rotational mass units in the modified end groups of the molecule, plus half of the number of units in the modified interior groups, with appropriate adjustments in special cases. Okay, that'll do it for today. Thanks for tuning in, and